In the last video, we talked about how energy can be transferred between the system and the surroundings, and we also introduced the concept of enthalpy. In this video, we'll continue the discussion on enthalpy and also talk about the method used to measure enthalpy changes, which is called calorimetry. So how do we know the values of specific heat, molar heat capacity, enthalpy of fusion, and enthalpy of vaporization? So as I just mentioned, the method to measure those values is called calorimetry, and it's an experimental determination of the quantity of energy transferred during phase changes or chemical processes. So for example, when a reaction is taking place, we can measure the heat that is evolved in that system or the heat released, or we can measure the heat that is being taken in by the surroundings by measuring the temperature of that particular reaction. So if the reaction is increasing in temperature, that's an exothermic reaction because the surroundings are getting hotter. If the temperature is decreasing, then that's an endothermic reaction because the temperature of the surroundings is decreasing. So to measure these properties of a reaction, we use what is called the calorimeter, and that's a device used to measure the absorption or release of energy by, again, a phase change or a chemical process. And we'll talk more about how a calorimeter works as we progress through this video. So when a reaction takes place, it can either absorb energy or it can release energy. And the amount of energy that is either released or consumed by that reaction is going to depend on a couple factors. First of all, how much reactants are there in the first place? If there are more reactants and it's an exothermic process, for example, then that is going to release more heat than the same reaction that has fewer reactants. And that makes sense because if we, say, had a small balloon that was full of hydrogen and oxygen, and then we just introduced a flame to it, lit it on fire, and that would result in a combustion reaction, which would release some heat. But of course, if we had a much larger balloon, maybe like a hot air balloon or the Hindenburg, for example, if that undergoes a combustion reaction, it's clearly going to release a lot more heat or a lot more energy. And the other property that's going to determine how much energy is released or consumed is going to be the enthalpy of the reaction, or the delta H of that reaction. So the delta H of the reaction depends on the difference between the enthalpy of the reactants and the enthalpy of the products. So here's another example of how the enthalpy of a reaction is dependent on the amount of reactants in a particular reaction. So let's consider this reaction here. This is a combustion reaction, so it's going to be releasing energy. So the amount of energy that the reaction releases as written is minus 5,754 kilojoules. The minus there tells us that it's an exothermic reaction. Now if we use half the amount of reactants, as in this reaction here, we have half the C4H10, half the oxygen, which results in half carbon dioxide and half the amount of water produced. In that case, the delta H of reaction is exactly half of the previous reaction. So this means that enthalpy is an extensive property, right? You learned about that in General Chemistry 1. I think that might have been in Chapter 1, actually. So the amount of heat produced depends on the amount of reactants used and the amount of products formed. So a common experiment that's done in general chemistry labs uses a coffee cup calorimeter. And in this particular experiment, which I think you'll be doing in lab, you will be using two nested styrofoam cups. And these particular calorimeters are useful for determining delta H of reactions in an aqueous solution. So for example, if you have a specific acid-base reaction that you're doing, you might start with the acid in the calorimeter, add a little bit of the base, and then you'll be measuring the temperature of that reaction as it proceeds. So we've seen this equation before in the previous video, except this time we're talking about the Q of the calorimeter, not just Q in general. And since we're using a coffee cup calorimeter and the reactants are going to be an aqueous solution, we can approximate the specific heat of that aqueous solution as being the same as the specific heat of water, which is that particular value there. And then, of course, if we want to continue to solve for the energy or the Q of the calorimeter, we need the mass of water that we use, and we also need the change in temperature. So the change in temperature, delta T, is going to be the difference between the maximum temperature the reaction reaches and the temperature that the reaction started at before any reaction had taken place. So let's go through a quick example using a coffee cup calorimeter. So in this question, we're doing an acid-base reaction where 200 milliliters of an acid is mixed with 200 milliliters of base in a coffee cup calorimeter. And we're given a temperature change, and we're also given the densities of the solution. And given this information, we're asked to find the value of delta H of the reaction for the reaction that's given below. So one thing we have to realize with any calorimeter problem is we are going to be measuring the temperature change of the surroundings, but we want to convert that or relate that to the temperature change of the reaction itself. So from the previous video and earlier parts of this chapter, we know that delta H equals Q, but it depends what delta H we're talking about, right? If we're talking about delta H of the system, that equals Q of the system. And if we want to compare delta H of the system to Q of the surroundings, right, delta H of the system is going to be the opposite of the surroundings, right? So delta H of the system equals minus Q of the surroundings. Now the same thing applies to a calorimeter. We're asked to find delta H of the reaction, but when we calculate Q, we'll be calculating Q of the calorimeter, which is part of the surroundings. So delta H of the reaction is going to end up being minus Q of the calorimeter. So the first thing we're going to do is calculate Q for the calorimeter, and then what we're going to do is relate that to Q of the reaction. And since the calorimeter is the surroundings, the reaction is going to be the system. And we also have to realize that when we determine Q of the reaction, the units are going to be in kilojoules, and they're going to be related to the amount of reactants that are used. So in this case, we have 200 milliliters of each with a density of 1 gram per milliliter. So the total mass of the solution is going to be 400 grams, but the units of delta H are in kilojoules per mole. So we're going to have to convert Q of the reaction into delta H of the reaction in terms of kilojoules per mole. So let's start off with the equation from the previous slide, because our first step is to determine what Q calorimeter is. So since it's a coffee cup calorimeter, it's an aqueous solution. The specific heat is going to be the same as that of water. And the mass, as we just mentioned, is going to be 400 grams because we have 200 milliliters of each of the acid and base with a density of 1 gram per milliliter. And then the temperature is going to be the difference between 23.48 and 22.15. So let's just write that out. Okay, so we've calculated Q calorimeter, but remember Q calorimeter is that of the surroundings. We want Q of the reaction, so then we can relate that directly to delta H of the reaction. So remember, this is going to be the opposite sign for Q of reaction. So we can write then that Q reaction equals minus 2.224 kilojoules. Okay, so remember now that this was the amount of heat release for 400 grams, and delta H of reaction needs to be calculated per mole. So the units of delta H reaction are going to equal kilojoules per mole, right? Now since delta H reaction equals Q reaction, we already have kilojoules, so that's going to be minus 2.224 kilojoules. And we're going to divide that by the number of moles of the reactants, but we have to know the number of moles of each of the reactants, right? So 1 mole of HCl reacts with 1 mole of NaOH. So we don't need the total moles of HCl plus NaOH. We just need to know how many of each of them react. So we'll look at them individually, and that's what's going to be going in our mole calculation. So if we want to calculate moles, each of the reactants is 0.2 liters, and we know the concentration of 0.2 moles per liter, so 0.200 moles per liter. Liters cancel out, and then we end up with minus 55.6 kilojoules per mole. Another type of calorimeter is called a bomb calorimeter, and it is mostly useful for determining the energy released during combustion reactions. So basically what it is just sort of a big bucket that has a bomb inside of it. So this bomb right here is made up of steel. It's kind of a screw top, and inside there is where you would put a little pellet that you know the mass of your particular compound that you want to burn. So the little pedestal that the pellet is placed upon is connected to some wire leads, which are then used to ignite the pellet. And the bomb itself is surrounded by water, and within the water there's a thermometer and a stirrer to make sure that the temperature of the water is homogeneous. So what you measure in a bomb calorimeter is the temperature change of the water, which is going to be related to how much energy is released by that particular combustion reaction. Now the bomb calorimeter itself has what's called the calorimeter constant, and this is the heat capacity of the bomb calorimeter and all the other insulated components within it. So the energy lost by the reaction mixture, so the little pellet within the bomb there, is going to be equal to the energy gained by the calorimeter. And we can use this equation here to determine what the calorimeter constant is. So here's a quick example determining the heat capacity of a calorimeter. So in this question we're asked to determine the value of C calorimeter if we know that burning 1 gram of benzoic acid increases the temperature by 7.248 degrees Celsius. And we're also given how much energy is released during this combustion reaction. So using the equation from the previous slide, C calorimeter equals Q calorimeter over delta T, we can determine the calorimeter constant. So the Q of the calorimeter is 26.38 kilojoules, and the change in temperature is 7.248 degrees Celsius. So if we solve this problem, we end up with a calorimeter constant of 3.640 kilojoules per degrees Celsius. Okay, so delta H is not always easy to determine experimentally, and one of the main reasons for that is that some reactions, when we mix two reactants together, they may result in more than one product. And if we're trying to figure out the delta H of one of those products, it's going to be difficult if we can't isolate each of those products individually. So in order to figure out the delta H of those types of reactions, we can use something called Hess's law. So Hess's law basically states that we can add up the delta H's of reactions that we can determine the delta H of in order to find the delta H of another reaction that is more difficult to find that delta H. So for example, if we know the delta H of this reaction and we know the delta H of this reaction, we can use that information to determine the delta H of this reaction. So delta H3, which is the one for the reaction we're interested in, is going to be the delta H of reaction 1 plus the delta H of reaction 2. So here's an example where it's difficult to determine the delta H of one of the reactions. So I want you to take a look at both reaction 1 and reaction 2. Notice that they have the same reactants, but they have different products. That's why it's difficult to determine the delta H of one of these reactions. Right? So we don't know the delta H of reaction 2. We do know the delta H of reaction 1 and reaction 3. So what we can do is to add up reactions 1 and 3. This is reaction 3 and this is reaction 1. We had to double reaction 1 in order to make some of the reactants and products cancel. Okay, so if we look at both of these reactions, we notice that carbon dioxide is a reactant on one side and a product on the other, so that cancels out. We also notice that oxygen is the reactant in one reaction and the product in another reaction. So if we add these two reactions together, we get 2 carbons plus oxygen producing 2 carbon dioxides. And if you notice, that is exactly the same as reaction 2 up here. So we can use reactions 1 and 3 to determine the delta H of reaction 3 by using this equation here. Delta H2, which is the delta H of reaction 2, is going to equal the sum of the delta H's of reaction 1 and reaction 3. So now let's talk about standard state conditions. So the standard enthalpy of a reaction, or delta H naught of reaction, is associated with a reaction that takes place under standard conditions. So standard conditions are listed here. So gases have to be at 1 bar, which is approximately 1 atmosphere. Solutions have to be 1 molar concentrations, and temperature is going to be 25 degrees Celsius. And the standard state of a substance is its most stable physical state under those standard state conditions. So oxygen is a gas at standard state conditions. Under those same conditions, water is a liquid, and carbon is a solid, and its most stable form is graphite. So going back to the example we saw previously using Hess's law, we can use standard enthalpies of reaction to determine the delta H of reaction at standard state conditions for this process that is used to form hydrogen gas from methane and steam. So this is the same diagram we saw before, but now we have numbers associated with it. So delta H1 at standard state conditions, delta H naught, is plus 206 kilojoules. That plus tells us that it's an endothermic reaction. For reaction 2, delta H naught at standard state conditions is minus 41 kilojoules. The negative tells us that it's an exothermic reaction. And if we add those together, delta H3 at standard state conditions is going to equal delta H1 plus delta H2. And the result we get out of this is plus 165 kilojoules. So overall, this reaction here is an endothermic reaction because we have a positive delta H of reaction. So the enthalpies that we've been talking about thus far have been delta H of reaction and delta H naught of reaction. Now neither of those take into account the number of products that are formed. It's just for a particular reaction, you would get a different delta H of reaction. Now the delta H of formation, delta H naught subscript F, is the standard enthalpy of formation, and it's the enthalpy change that takes place at a constant pressure of 1 atmosphere when 1 mole of a substance is formed from its constituent elements in their standard states. So if we have these two reactions at the bottom of the slide, this reaction here, notice that it produces 2 moles of nitrous oxide. And in that case, under standard state conditions, it would have a delta H naught reaction of 180.6 kilojoules. The delta H of formation is going to be that reaction when only 1 mole of nitrous oxide is formed. Okay, so these two reactants are the reactants in their standard state form, and they form 1 mole of a product. So that is our delta H naught of formation, and that ends up being half, in this case, of the delta H of reaction. So we can use the standard heats of formation to predict the standard heats of reaction using Hess's law. So for example, if we have this reaction here, and we want to determine what the delta H of reaction is, we can use other reactions which consist of the reactants and products of this reaction to help us determine what delta H is. So in this case, we've chosen 3 different reactions. And if you notice, in each of these 3 reactions, you can find the reactants and the products of the overall reaction above. So reaction 1 has methane, which is up there. Reaction 2 has both oxygen and carbon dioxide. And reaction 3 has oxygen and water. Now, one thing I will say about your slides, you're going to have to correct this right here. There should be a negative in front of that 74.8. So since we know the delta H is of formation for all of these reactions, we can use that to try and predict the delta H of reaction using Hess's law for the overall reaction here. So the first thing we need to do is to make sure that the reactants and the products are on the right side of each of those 3 equations. So the first reaction, if you notice on the previous slide, it had methane as a product, but in the overall reaction that we care about, methane is a reactant. So we have to reverse reaction A, and when we do that, we also change the sign of delta H. So delta H formation there ends up being positive. Reaction B can stay the same, and reaction C, notice that we've doubled the reaction. And we'll get to why we did that in just a second. So now the next step is to see which of the reactants and products are the same on either side of these reactions. So for example, in reaction 1, we have carbon as graphite as a product. In reaction 2, we have carbon as graphite as a reactant. So since the carbon is present as a reactant in one reaction and as a product in another, we can cancel those two out. We can do the same with hydrogen. So hydrogen in reaction 1 can be canceled out with the hydrogen in reaction 3. Now the reason that we doubled reaction 3 was so these hydrogens would match in stoichiometry. If we didn't double it, we'd only have one hydrogen and wouldn't be able to cancel out the 2 hydrogens in reaction 1. 2 oxygens, and those are the reactants, and our products, carbon dioxide and water, right? So we've canceled out graphite, we've canceled out hydrogen, we've canceled out graphite, we've canceled out hydrogen, and then we're left with the overall reaction, which is shown down here, which is the same as the reaction on the previous slide. And now all we have to do to figure out the delta H of reaction is to add up all the delta H's from each of those 3 reactions, and that's shown in the last equation here. So once we do that, we end up getting a delta H of reaction as minus 802.3 kilojoules. Now we can do this process mathematically as well. So the process of calculating delta H of reaction from delta H of formation can be done using this equation right here. So basically all we're doing is we're taking the delta H of formations of the products, multiplying them by their respective stoichiometric coefficients, and subtracting that from the delta H of formation of the reactants multiplied with their respective stoichiometric coefficients. So if we were to consider the same reaction on the previous slide, which is this one right here, since we know the delta H of formations for each of the reactants and products, we can write out this equation here, which, when we do the math, ends up giving us the same answer as we had in the previous slide. So I'm going to go over a quick example just to show you how this works. In this question, we're asked to use the appropriate standard enthalpy of formation values from table 10.4, which is on slide 14, to calculate the delta H of reaction at standard state conditions for the complete combustion of propane, which is given by this reaction here. So if we take a quick look at table 10.4, we can see the delta H of formations highlighted here. So I've reproduced those here, and now all we have to do is use our equation to determine what the delta H of reaction is. So the delta H of reaction is going to equal the sum of the delta H of formation of products minus the sum of the delta H of formation of the reactants. So the 2 products are carbon dioxide and water, which are right here. And notice that we have 3 moles of carbon dioxide and 4 moles of water, so we're going to have to take those into account when we are doing this calculation. So we'll do carbon dioxide first. So we're going to have 3 moles of carbon dioxide times minus 395.3 kilojoules per mole. And we're going to add to that 4 moles of water times minus 241.8 kilojoules per mole. And from that, we're going to subtract the reactants. So our reactants are propane and oxygen. So we have 1 mole of propane and 5 moles of oxygen. So we're going to have 1 mole times the delta H of formation of propane, which is minus 103.8 kilojoules per mole. And we're going to add 5 moles of oxygen, but oxygen is 0 kilojoules per mole, so that is not going to matter. So if we complete this calculation, we end up with an answer of minus 2043.9 kilojoules. That's all I have for this section. If you have any questions, please feel free to contact me.